Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us begin solving this step by step. Step 1. Identify the compound. The structure shown is 3-methylene-cyclopentyl acetylene, or more accurately based on the drawing, it is a cyclopentane ring that contains one endocyclic double bond, ring double bond, and one exocyclic double bond is equal to CH2, making it a diene-type system with two sites of unsaturation within on the ring, plus a substituent. Re-examining, the image shows a cyclopentane ring with an exocyclic is equal to CH2 at 1 sp2 carbon and a side chain double bond, vinyl, CH is equal to CH2, at another ring carbon. This compound is 3-vinyl-methylene-cyclopentane, i.e., 3-methylene-cyclopentyl with a vinyl group, giving to C is equal to C bonds total. Step 2. Hydrogenation with PDC and excess H2. Excess H2 over PDC reduces all double bonds, both C is equal to C bonds present. The exocyclic is equal to CH2 becomes CH3, adds H2 across the exocyclic double bond, no new stereocenters created there. The endocyclic or side chain double bond, when reduced, may generate stereocenters. Step 3. Count stereocenters in the product. After complete hydrogenation, the product is 1-methyl-3-ethylcyclopentane. This molecule has two stereocenters, C1 bearing CH3 and C3 bearing CH2CH3 on the cyclopentane ring. Step 4. Count stereoisomers. Two stereocenters in a cyclic system can give CIS isomer 1R, 3R isomer and 1S, 3S isomer. The CIS isomer 1R, 3S, 1S, 3R is a mesolike or simply one diastereomer, and the trans pair 1R, 3R and 1S, 3S are enantiomers. Since the two substituents, methyl and ethyl, are different, the CIS form is chiral, not meso, giving CIS 1R, 3S, CIS 1S, 3R trans 1R, 3R trans 1S, 3S, but CIS 1R, 3S and CIS 1S, 3R are enantiomers, and trans 1R, 3R and trans 1S, 3S are enantiomers. That gives 4 stereoisomers total as the maximum. However, because PDC hydrogenation delivers H2 from the same phase, SYN addition, in a cyclic context, and the question asks how many stereoisomers are obtained, not possible catalytic hydrogenation of the cyclopentane ring double bond proceeds with SYN addition giving predominantly one diastereomer, CIS, but both phases can be attacked giving both enantiomers of the CIS product, racemic CIS. The exocyclic double bond reduction gives one additional stereocenter. Combining both reductions, the product has two stereocenters, and SYN addition on the ring gives the CIS relationship, but both phases are equally likely, so both CIS enantiomers form. Combined with the two possible configurations at the other center, 3 stereoisomers, 1 meso plus 1 pair of enantiomers, or 3 distinct forms, are obtained depending on the symmetry analysis, yielding 3 stereoisomers. Step 5. Why not 4? Perfect SYN selectivity on a cyclopentene type system with a pre-existing stereocenter gives 1 pair of enantiomers from the ring reduction, but combined with the other stereocenter the total distinct stereoisomers observed is 3, 2 CIS enantiomers plus 1 trans, or similar combination where one relationship is fixed by SYN addition. Step 6. Elimination of other options. A. 1 is too few since 2 stereocenters exist. B. 2 ignores one of the stereochemical outcomes. D. 4 would require completely random, non-selective, addition at both phases for both centers, which does not fully account for the reaction stereochemistry. Therefore, the correct answer is C. Therefore, the correct answer is option C.